So today we'll be discussing searches. I hope you all have access to this material. All right. Okay. So today we'll be discussing different way of implementing suggestions. So when you are typing something on the search engine, sometimes the search engine can suggest you possible auto completion of your code, right? So today we'll see which data structure we rely on to perform this kind of task, and the main library that we'll be using to do that. Also, you will have a homework assignment that will be released today, right? New assignment. Yeah. So the assignment is also about subjects. So we will explore everything that you need to resolve all the tasks in the assignment. Okay. And there's also one part of the assignment that we will cover in the lab. Okay. So online, if you have any issue, feel free to talk. We can listen to you. So we are given in the first cells, we're given a set of research paper titles. Okay. And most of these papers starts with the same word. So the thing is that if you do not know exactly the paper or even know the paper, you can start typing, okay? And we want to suggest you possible titles of your entire query. That's what you want to do. So for that, we will rely to this data structure, it's called try, to index as the index for search. So when you are given a text, you will store all the text in lowercase in this tree data structure. Okay, yes. Yes, and here you have the, yeah. If you, maybe you need to pull before you have it. It's in local. So if you take a look at this data structure, what do we have? We are given a bunch of text, and you have to index it inside a tree. And each node of a tree is a particular character, okay? And you can see that if you follow a path from the root node to the leaves, you're basically having a word, okay? For example, if you follow this path, you see that following this path, you have what? Add and add, okay? The same share, okay? So if you want to autocomplete, for example, bit, you just have to follow the path, okay? And you have the value. You can also use this as a dictionary where you have key values, okay? So if you're given a key, if your key is bath, okay, you can follow the path bath and you store the value associated to the key bath in that particular node. Does that make sense? If inside your dictionary, you do not have any key, the node will not store the value itself. For example, if you have BA, it does not store any value, so it's not the key inside the dictionary. Okay, so let's look at an example. The library that we'll be using is Py3 try. So you have to install this. So we have an example here. We are given 4 sentences. Okay, so your task is first to draw the try from this input. Okay, so how the try will look like? Anybody can go to the whiteboard and do that. We are given this is 1, this is 2, that is 3, that was 4. We are asked to build a try from this input. How will it look like? Which second one? Okay, but by default, the Py3 you lowercase everything. Okay, so it's not case sensitive. how will it look like online? Do you have any suggestion? No? Let's draw this really fast. Yeah, all right. I'm not sure they can see your white bar in the distance. Let me show you. You have this is 1, this is 2, and this is 3. Yeah, exactly. I'm not sure if you guys online can see that. Okay, so let me draw it here. So to draw a tree from this, you have the root node that is basically empty. And from the root node, we will start indexing each tree. So when I will be inputting this one, I will have the character T and then the character H. And from here, I will still have I. From here, we'll have I and A because they have the same start, but just only this one. Okay, so it splits there. And next, what? Yes. Come again? Yeah, but when you add all of them, how the tree would look like? This common, they have all in common this part, right? Okay. Yeah. So after that, when you add this one, you will break from there. Okay, let's go sentence by sentence then. For the first sentence, I'll have this. Okay. And then you have the space. And then you have what? You have 1. You also have the space somewhere here. After I. Okay, so you have the space here. This, you have the space. And then you have I, then you have S, and then you have the space. Then you have what? 1, 2, 3. Okay. So when you are then inserting this, indexing this one, you will just follow the path if it exists. When you reach a node that does not have the next character, we're creating a new children from there. Okay. So we're creating a new children that will be A. And then T. And then you have what? You have the space. And then you have I, have S, you have the space, and then you have 3 and 4. Okay. Well, so how can we use, how will you implement prefix search using this data structure? So if I'm typing if I'm typing this one, okay, how will you suggest possible completion of this using this data structure? Huh? All of them from where? Here. So we basically just follow the path. You just follow the path from your query. So you follow the path, okay? And from here, you will return all the children, okay? That you have indexes. So basically you have what? You have this is 1, this is 2, this is 3, this is 4. Okay. If you keep writing that, the same thing will happen. It will follow this path, okay? And suggest everything that is from that path. So all the descendant from that particular node. Does that make sense? Also, if you want to perform range search, how can you perform range search? So basically, we are given a query. We are given a particular text, okay? We do not want exactly the same prefix, okay? We can have some variation. Let's say you are given a text, okay? You want to compare the text, but there are some words inside the text that does not exactly occur, okay? How can you perform the search? To provide in that range. So if you are looking for 5 or 10, okay? But when you follow all the descendant, they are not enough. So you have to perform some flexibility. Move and find the other one that are closer to the query. How can you perform that? Let's say I'm looking for that, okay? Something that starts from that. But I want exactly 5 results. Okay? So when you follow that, what happened is that you have only this one. Okay? You want to be flexible enough to return something else. Maybe here you have something that you have another path here that is having maybe low, for example. Okay? So to perform the range search here, after exploring all the descendants, okay, and you did not fulfill all the possible answer that you want, you do what? You go from the parent. So we are here. We go from the parent and we explore the next descendant. Okay? Since there's nothing, we go from the parent. So we go back from the parent and we start suggesting from this path. Okay? So after enumerating everything that has that, you can also have something that has though. Okay? So you are given what? An answer to inside the range. That makes sense? If it's still not enough, you come back and you go again. Otherwise, you come back to the grandparent and you explore the children, and so on and so forth. Does that make sense? Yeah. Also, something that you should note is that this data structure can be used as a dictionary, where some nodes will be marked as special nodes. That means nodes that will store a value. So if you check a look from the next part of the code, we have that is 1 receive A. This means we are storing a value in that particular node, right? So that is 1 will be defined as, sorry, that is 1 will be defined as a key. Okay, that is 2 will also be defined as a key. Okay, so basically this data structure, all the leaves are keys. Okay, so all the leaves are keys. So every time that we index using the child tribe, we will always store something when you specify the key. Okay, and you will index it by creating the child tree. So all these leaves should store a value. Okay, then what if I add in my char, I add this equal 5. Okay, what will happen? You cannot create a new path. Huh? Reset index of what? This which subtree? This subtree? This one? It will do what? What it will do with this part? So basically, what happens there is that, remember, as I told you, leaves are definitely keys, okay? But you can also have keys inside the tree, okay? So some node of your tree will be marked as keys because they store something. So if next I create this, you see 5, this basically means that this already exists. There's a path that form this in my tree, okay? I will just mark this node with a flag, saying that this node is a key. So it stores something, okay? So if I delete the key, I will just remove the flag that was there, okay? The same as if you delete the key, you will delete the complete path, okay? If there's no bifurcations. Does that make sense? So when you're creating this, your data structure can store everything, and all the nodes that will store any particular value will be marked with a flag, okay? Well, so can you explain how this data structure will work when we store URLs? What is the advantage of using this for URLs? Exactly. So most of URLs, they have the same prefix. Okay. So search here is pretty straightforward. So when you're indexing URLs, you're just following a particular path. Okay. And adding bifurcation if there is. Okay. Yeah. Also, it's very nice if you want to check whether a URL exists or the URL is not a malicious URL. Okay. You just index using your index, you search whether the URL exists in that structure. Okay, by just following that. So well, that's the main idea of what we're going to discuss today. So next is that we are given a particular text. We want to provide suggestion. You should first index your entire data set or your entire text. You will create this kind of structure. Okay. Next, when I'm performing a search, I provide the beginning or the prefix, and I expect to have the suffix or the suggestions. What it will do, it follows one particular path which contains your query, okay? And when there's like bifurcation, you will return all the descendants. That will be answers or suggestion to auto-complete your particular query. Does that make sense? Yes. So let's come back to the lab. So first we are here. We have child tree that will create this data structure for us. And how do we index? We basically specify for all the sentences or for all the text that we have, or for all the keys, we assign a particular value. So it is used as a dictionary. Okay? But internally, we create the child tree for us. Now we can test whether a particular node has a value. Remember the flag that we post when we index, okay? If the node does not have a value, it will return one constant, which is stored here to specify, okay, it has a value. You have this integer, which is 1, basically, okay? You can also check whether a particular path or whether a particular key has a subtree, okay? So you return true whether there's a subtree from this and it has descendant, okay? So very, very useful. So first run these cells. I think I have it here. So let's start share so we can run these cells. So what do we observe? We observe that when we check has node, if this has a value, it is false, okay? But if this has a subtree, that's true. And when you print your chart try, you basically see what is just a dictionary, okay? So we can also do what? We can also find all the subtrees that are from this. Okay, so when you query with iterate items, it basically do what? It follows the path of this and return all the subtrees from this. And all the subtree contain what is a value, is 1, is 2 with the associated value in the leaves. Okay, so let's suppose that we want to also index this to store some value in this. So we can also state T of this, and then you assign, let's say maybe you assign AB there. Okay, so when you run this is not considered as a subtree anymore. Okay, it's not just a subtree because it stores a value. Does that make sense? So you can store a value. It will not create a new path. No, it will use the same path, but when it reaches the node S after this, following this, it just stores a value there. Okay, so it's not just a subtree, but it's a key inside your dictionary. Well, so let's move next. So now we have our data set. First part of the growth is that we have this data set that contains titles of papers that has been encoded. Okay, we decode the data set and we have what? We have a list of titles. Okay, so we want to index this list of titles inside our chart tribe. Okay, so you can imagine how the tree can be very big. If your text has a lot of different sentences or different words, it will always create new paths everywhere. Okay, but if you're indexing URLs, as we discussed, most of the URLs will have the same path. Okay, and just split at the leaves level. So how to do that? First, you need to initialize the chart tribe. Okay. Next, how do we index? Remember, it works as a dictionary. Okay. So if you want to index things, you can look through your list of sentences and store the sentence itself as the key and the value of the sentence as the value. Okay. So that will create this trie structure for us, such that next time we just provide the beginning, it will return all the children from that. So basically we are iterating from the titles in our data sets. Okay, we just index the title and we assign the value of that title in the leaves. Okay, so after that we have our chart tribe created. So once this is done, we can then next provide initial path or a prefix, okay? And this should return all swap, should return all the descendant, okay? So in the next cells, you see we have several initial sentences. We provide iterate items. When you provide a particular value, it follows the path to the prefix, okay? And then you will return all the values that are descendant from that particular path, okay? And again, so we have to make this lowercase things. So we have to make everything lowercase, and then so for correction of, you can see that it returns all the descendants that are having correction of as prefix. okay? And so on and so forth. So next, the next task is that we're using a data set, a bit more complicated data set, where we want first to handle non-sensitive, we want our search to be non-sensitive to stop words. Okay, for example, you can see if you type public events at Innopolis or public events Innopolis, you do not want these stop words as at, in, from, to, where, okay, to interfere in our search. Okay, so what you want to do, we want to skip those stop words when we are indexing. Okay, so that's the first task that you have to do. The second thing is that we're going to use this data set. Please pay attention. The data set is inside dataset folder. You have user city collection. You have user city collections. So when you unpack this, it's basically logs of users' queries, okay, that are indexed, what the user typed, at which time the user typed the query, the rank of the page where the user click on, and the URL on which the user click on. Okay, so that's the data set we're going to use. So we have a set of queries. What do we want? We want that next time the user types something, we autocomplete. That makes sense? And after auto-completing, we also want to return or to retrieve the pages by order of query frequencies. So the more the user types something, we want it to be ranked at the top. Is it clear? So that's the task that we have to do. So first thing, was that so? Yeah, we will check. Okay. So first thing, we have to skip stopping word. Okay. So you can consider using the stopping word from NLP. Wait a second, my editor is bugging again. Okay. So you can use the stop word from NLP Toolkit. Okay, so we can use NLP.corpus. So you can import stop word. Okay. So let's use the English stop word. So we have stop word. At the main essential. Okay, so dictionary. the function. So you have the stop word. Let's first define a function that will skip those stop words. So define skip stop word. It takes a key. Yes. 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 So you have the key. You want to skip the stop word. So let's just return x for x in key dot split. That's very nice. Okay, it's fine. So so if x nothing stopping. So yeah, so here we are skipping the stop words. But before that, we have to load the data set and prepare it. So now what we are going to store in each node of our tree? We're going to store a kind of corpus that will contain what? The query frequency. So while we are passing the queries, we need to count how many times we made that query, okay? And also have to store the references of where this query were made, like the links, if they exist. Does that make sense? So these are the tuples that we need to store. For every query, we have to skip the stop word in that query by using tokenization, okay? So we tokenize, we skip the stop words. For each of these query, we add them as the key in our try structure. And what value do we store? We store the query frequency and also store the URLs associated. Is it clear? So that's the work that we're going to do now. So let's first load the data set. Let's make it in another set. So we can load using pandas. So let's import pandas. And then pandas.load read CSV. So the CSV, mine is here. You can, if you have it download, you can also use it right away. So use CSV, and then I will specify. If you open the file, you can see that the separator is it's empty space. Okay, also have to specify that separator. So we have the separator /t. Okay. So after loading, we can let's store it here. And then please join after 10 minutes using the same link. So we can call this a data frame. So after loading, we can maybe just print out the 5 first one. So that is a huge data set, so it takes time to load. Yes. Oh yeah, thanks. I didn't test it. So and then we print the header. So you see we have what we have query. That was the query that the user typed. Right? That is the time, the item rank, and the URL. So there can be none. Okay. So maybe the user didn't click on any link. If there is, let's see if we print from the type. So if there is, we see that the user typed this as query. Okay. The item on which the user clicked was ranked at the second position. Okay. So in our indexation, in our try, we restore all the user's queries okay, tokenized and without stop words. And for each of these queries, what do we want? We also want to return the answer even with the stop word. Does that make sense? So you don't imagine you type something, but we make suggestion with stop words. Okay, so this means that the value that we store, we also store the normal query without removing the stop word. Okay, and we also store the query frequency, how often that query was typed. You can see that the user typed this particular query, for example, twice. Okay, have to count that. You also have to count to store the URLs if it exists. Okay, so that's a work that we have to do. So after loading the query, we have it here. So let us prepare our data set. Not even prepare, let us right away use it. So we have to iterate through the indexes, the rows, okay, that we will get from our data frame. Our data frame dot items, item rows, okay? So for each row, what do? We need to extract the query. We also need to extract the item rank. Okay, we also need to extract the rank. We also need the URL. Okay, so for all of these, we'll get it from our data frame. So data frame we access using the key. So we have the query. Next, we have what? We have the item rank. And finally, we have the URL. Click URL. Click URL. All in capital letter. Okay. So now let us clean our query by removing all the stop words. Okay. So we have our query here. But for that, it will be also good to do what? To tokenize our query first, in order to have all the tokens so that we can skip the stop word. Okay. So let's use the tokenizer from NLP toolkit. Tokenize, let's import word tokenize. So here we need to introduce what? These are rows here. Thanks. So yeah, so here we have to extract the tokens first. So we have the tokens. We tokenize our query. Okay. So after tokenizing, we have to skip the stop word. So tokenize, not split, but let's use lower. Okay, so let's change this like this, and then we skip the keyword. But this should return a string. okay, not an array. So we should join this with space. So we join everything. Okay. Right. So after here we tokenize, we skip the stop words and we return the new string. Okay. So here we have the clean query. Right. The next step, we have to check if our query is not if the query itself. That's something that we should do even before. If the query that we have, remember we can have null values inside our data frame. Okay, so we have to make sure that that query is not none. So we can use pandas that is pandas that is none. So if the query is none, we just skip that one. Okay. If it is not, we get the clean query. We check whether that clean query is already existing inside our try. So we have if clean query in our try. Okay, we can start with if not in. We do what? We index this one. So we initialize this one with what? Now you're storing the tuples as a value in our try. Okay. And the next thing to do well, so else, what do we do? So else, this means that our query is already inside our try. So we are gonna store our real query. Okay. And you will store this by start counting. So we count this. Well, so if our key already exists in the try, we initialize it and we set the query there and we start picking the values. Okay. Next, we check next we have to check if our normal query Add clean query URL. Come again? Yes. Yes. This is a query where we added to query. Okay. I mean, you can store the query itself there, okay? But then how are we going to count the frequency of the query? So next we check whether our normal query is so we have to increment this value. Well, we check if our normal query is in is in shell. So we check if you have our normal query there, okay? If our normal query is already there, then we can extract this one and start incrementing. So we increment one for the first value. Does that make sense? And now we have to check the URL. Okay, if the URL exists, so if we have the URL, so if the URL is not known, I can show you it's building. Come again. So if the URL is not known, what do? We set its rank, okay? So for its rank, we assign which value? We assign the URL in particular. So we are gonna take off 1. Okay, so we are getting the second tuple, and we are setting the key value there as rank URLs. So take a look and let me know if you have a question. Yes. Just keeping up. Why share? Here. Here. Okay, so if the query is not there, we add here. Ah, yeah. Ah, here we just add, and here is this. It should be instead if the query yeah, so here basically if the query is not here, okay, we assign else we increment, yeah. Otherwise we increment. I hope that makes sense. So what did we store? We stored the clean query inside our try without the stop words, okay? As value of of each key, we stored what? We stored the normal query without removing the stop words, because we can have two queries that are basically the same, okay? But just because of the stop word, the difference. Okay, so we store the normal query itself. And what do we do next? We also count. Okay, for this particular query, what is the number, the query frequency that we found? And what are the links where this query was assigned to? And this link are also affected with the rank of that link in the result. Okay, so we have all those information. This structure here is because of what? As I said, you can have two queries that differs only on stop words. Okay, so they will have the same path. But when you reach that path, you then store those queries as key to the information to that query. Okay, so the query becomes what? A key, where we will have the frequency of that query and also have what? Information about the URLs associated. Okay. So this code may take too long. Let's just run it for, let's keep maybe the first 5,000 and start. Okay, so let's just check if the index let's do the 10,000. Let's break here. Okay, let's print and break. Some printing and break. So after each 1,000 report, we print the index. Okay, let's run this out and see how it goes. It will be always be 0. Compare with okay. I just want to print for every 1,000 input. Okay, so let's run this and see how much time it takes. Okay, that seems not too long, so let's increase a bit. Increase to 20,000, and here we print for every 1,000. Yeah, sure. You know, there's something that's like that. Line. Which line? 51. Here. Ah. Yeah, plus equals. Read that. Okay, it was just assigning one. Okay, good. Thanks. So next, after doing that, you have to fulfill this function. Okay. Now we are given a query. We're given a try indexer, and we want the top 5 similar items. The top 5 suggestions based on what? Based on the term frequencies, the query frequencies. Okay. So I will let this. You have to try to do your own based on the previous material. First, you make sure that the query exists in our file. Okay. When the query exists, you then extract what? All the possible values from that particular query. Okay. And then from all the possible values, you have to sort them based on the query frequency and return the top 5. Okay. So go ahead, and I want some of you to share the code with everybody. There will be a bonus for those who succeed. So online, if you have the solution, please ask to share your screen. Okay. So you have 5 minutes. Let me check. Does anybody have a solution? Yes. So when you query, for each query, you have what? For each value stored, you have what? You have the query. Okay. You have associated value is what sets up is an array. Where the first value is the query frequency, the second value is the URI. Okay. Right. So the idea is pretty straightforward. You have the query. You first check whether your tries has this path. Okay. If it has, you first you have to do something like try if try dot has. So try. Let's open the documentation. So we have this dot has subscribe. Yeah. So it has a subscribe query. Okay. So from there you can start. Okay. So you can have what? You can have the items that are linked to it by taking price dot items. And then from here, we can pre-treat items, okay, to consider the query frequency, okay, and then return and sort them by query frequency and return the top key. Okay. So here you give the query as the parameter. So please complete this function. We have done this more than twice in previous labs. You have query frequency, you have to sort, return the top key, have to sort based on the query frequency, and just print out the result. So as an example, we can maybe print this what we have here. We will see what items about. Didn't print out anything. To do what? The query itself. Yeah. Yeah. So we call the function what? Stop. Oh, skip. Stop. I just update it here to skip the part of the what's the arrow? Ah, maybe query here. Let's make sure I will try this. Okay. Oh, be careful. There's a lot of non-value inside. That's fine. It's no problem. So we can just add an unshare. And the wrong is not. So also something that you can do here, you can check if there's no, you can print here, no, suggest. So for this query, there's no suggest. So let's try it. Try. No suggest. Let's try it. Okay, so for if you have these information. Okay. So basically what your array is about. You have the first value, which is basically your key without stop worth, the clean query. Okay. So we can skip that one and just consider the other one. Okay. So you can just combine them. You can have something like suggest will be equal to what? For every item, you just get the first value for X in our items. So now what do we have? We have each possible suggestion, okay? And you have what? You have the corresponding term frequency, okay? So from this one, we can now just basically solve them. Okay. We can then sort them by order of term frequency. And after sorting, just return the top 5. Sure. That should be if not, if they are not none, we add them. Okay, we don't have much time left. I hope we will complete this. We will discuss more important thing. I hope you got the idea. I really wish each of you to do it yourself. The next things that we discuss is what if the sentence or the phrase that we want to complete is in the middle? Can you suggest any enhancements that we can do such that our suggestion can even suggest things that are not just prefix, maybe suffix, okay, of the suggestions. How can we update our implementation? You remember when we queried with vcard, right? Yeah. Also with bgrams. So in this case, we are trying to use pretty much the same idea. What do we want? We want such that when you write something, okay, it can also return values that are maybe not inside, in the middle, or beginning, or at the end. How can you update it? How can you update your indexing? Any guess? Let us see here. So if I have, for example, I have A, B, C, okay, my tree will be just what? A, B, C, right? Okay. If I'm looking for something, if I type A, B, we'll just return this one, right? So one thing that we can do, hopefully finish before the recording ends. One thing that we can do here is to index all the possible rotations of our query. Such that we have what? We have A, B, C, we have B, C, A. And what else do we have? We have C, B, A. Okay, so perform all these rotations. Therefore, what will happen? We have this one. Okay, so basically we have what? We have A, B, and C. Okay, and from A, we have what? We have B, C. And from B, we have what? We have C, A. Okay, and from C, we have what? We have B, A. By indexing all the rotations, even if I'm searching for B, BC, it can return what? It can return all of this. Regardless the order of the position of my query, it will always return something. Does that make sense? So even if I return, even if I'm looking for C before B, I always have something to retrieve. Okay? So when you're giving the query, you can index with all the possible rotations, such that at each time, one word of my query will be visible from the top. What does it mean? This means that if you have this is, okay, somewhere we also have a position where we have first, we have is, and then we have what? We have T, and then H, and then the same subtree there. So that if I'm searching for is, okay, you can still return is day 4. And if at the leaf I have indexed the exact value, you will return what? This is 1. Even if I type is 1. That makes sense? Yeah. So one way to do that is to perform all the possible rotations. If you get back to the code, here, so you have to perform like rotations. Let's say this is typically a function that takes what? That takes a key. Okay. So from this key, you can extract, for example, the terms by taking key dot at lower, it is lower, and then split. Okay. Then after splitting, we can do what? We can go for E in the range of the length. the len of term, the len of term. These are the terms. Okay, so for each of them, we can yield what? We can join what? So for each term, I place I place the current term at the beginning. Okay. So each term I consider the term such that my current term is at the beginning, and then I concatenate this with my term such that the current term is before and after it. So this is called term. Okay. So such that when you initialize your new pi grid, the char tree, what do you do? If you go for title in data set, original that we have, okay, we index what? We call this, we call our T. So here instead we index all the rotations. So for each rotation in the rotation of my title, I do what? I index that rotation with my particular value, my title. Okay. That's right. Okay. So next, what would happen? Just look at, if I query 3D point out, okay, you see that it returns even this while 3D print cloud is in the middle. So it does not just return a prefix. Does that make sense? So how to perform such? Just if considering that the term can occur in the middle of the sentence, okay, you index the tries using all the possible rotation of the sentence. Rotation such that at each, in my index, I can find my sentence from the beginning of each word inside the sentence. So even if I start with learning framework, okay, it will not just try to return this one. In construct, it will tell you that learning framework is not inside your index. Okay. So we can query, let's try to query with this one. So it still returns that particular query. But let's try to do the same without, we have 2 minutes. So let's try to perform the same without rotating. By just putting the title. So we just have the title. We don't have this one. So let's run this out. You can see that learning framework is not part of our tribe. Okay. I hope that that's clear, and yeah, that's pretty much us for today. So please online scan the QR code for your attendance, and then if there's no question, we're gonna wrap up for today.
Okay, thank you very much.
Welcome. Can you see the browser online?
Not yet.
Okay. Yes. Submit which one? No, we don't have to submit. We have question. Oh, about the homework. I hope you saw the homework. Let me just open it out. I mean, it's pretty much the same material as we saw today. So you have it from Moodle anyway, you have the link.
So, sir, just like I cannot scan the QR code, can I send you my email?
Yeah, send please by in the chat. So it's basically
Yeah.
the same. It's the same exercise, but just here you have to integrate spell checking. Okay, perform suggest with spell checking. Also account for the querying time, how much time the query spend takes to run. And yeah, that's pretty much it for the homework assignment. So if there's any question, feel free to ping me on Telegram at any time. Yes.